Okay, greetings math people. Today we're going to be talking about quadratic sequences. Let's go ahead and get right into it.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.
All right, so we're talking about quadratic sequences. So what's a sequence? So a sequence is just an ordered list of numbers. Quadratic sequences are not the most popular or most known sequences in the world. Probably those that you may have heard of are arithmetic sequence and a geometric sequence. To talk about those two just briefly, so an arithmetic sequence, that's a sequence where each subsequent number is found by adding what is called a common difference to the previous number. So every pair of consecutive numbers have the same common difference. An example of an arithmetic sequence would be the sequence 2, 5, 8, 11, 14, 17, 20, 23, 26, 29, 32, etc. so on. As you can see, as I go from 2 to 5 and 5 to 8 and 8 to 11 and 11 to 14, I'm adding a common difference. I'm adding the number 3 to go to each number. That's what makes a sequence arithmetic, when you add a common difference or you add the same number to go to each term. An example of a geometric sequence would be 2, 6, 18, 54, 162, 486, And what is happening there is you're multiplying by the same number to get each term. So I'm multiplying by a common rate of 3. As I go from 2 to 6 times 3, 6 to 18 times 3, 18 to 54 times 3. So that's what makes each of those more popular sequences. So how do we analyze the numbers of a quadratic sequence? Well, let's talk about why a quadratic sequence is called a quadratic sequence. And so I want to briefly mention or talk about the two sequences I just alluded to, arithmetic and geometric. And they have rules or an explicit formula that describes the sequence. I mean, a rule in terms of a variable n, where n is the number of the order of each term. For instance, I mentioned the sequence 2, 5, 8, 11, and so on. 2 would be the first term, 5 would be the second, 8 would be the third. And so when n is 1, I get 2. When n is 2, I get 5, etc. And so like the rule for that particular sequence, and it's written like this, it would be 3n minus 1. And so if you notice, if I plug in 1 for n, which would be a1, that would be 3 minus 1, or 2. If I plug in 2 for n, that would be a2. That would be 3 times 2, which is 6 minus 1, giving me 5. If I plug in 3 for n, that would be a3. That would be 3 times 3, 9, minus 1, 8, and so on. So as you see, I mentioned this deal called the common difference, where I was adding 3 to these numbers. We denote that with the letter D, and it's really the same as the slope of a linear equation, and basically. So this is basically just a linear equation, the arithmetic sequence. The rule for an arithmetic sequence, or the explicit formula, is just a linear equation where the slope is the common difference. And for the geometric sequence that I spoke of, and I think the geometric sequence I spoke of, the terms were 2, 6, 18, 54, and so on. The rule for it would be an equals 2 times 3 to the power of n minus 1. And again, if you just notice, if I plug in 1 for n, this would be 2 times 3 to the 0 power, which is just 2. And if I plug in 2 for n, this would be 2 times 3 to the first power, which is 6. If I plug in 3 for n, this would be 2 times 3 squared, or 2 times 9, which is 18, and so on. So what makes a quadratic sequence quadratic is that the formula of a quadratic sequence is that of a quadratic expression. So you may remember, or you should remember from your algebra days, a quadratic expression looks something like this: ax squared plus bx plus c. And so a quadratic sequence is of the form an squared plus bn plus c. So that's what makes it quadratic. Now, is there a way, or how can I tell it's quadratic if I'm just looking at the list of numbers? Because it's easy for me to tell if it's arithmetic. As again, I'm looking at the sequence I mentioned before, 2, 5, 8, 11. I easily can see that that's arithmetic. I keep adding 3. It's easy to tell if it's geometric. If I just use the example I used before, 2, 6, 18, 54. If I just look at those numbers, I can see I'm multiplying by 3. It's geometric. So is there a way to look at a quadratic sequence and determine if it's indeed quadratic? So let's look at it. So here's an example of a quadratic sequence. So here's a quadratic sequence, 18, 46, 90, 150. And so if you look at these terms, obviously I'm not multiplying by the same thing, of course, because that would make it geometric. And obviously I'm not adding by the same thing because, of course, that would make it arithmetic. So what is happening with these numbers? So we do want to look at what we're adding to get each number. For instance, as I go from 18 to 46, I'm adding 28. As I go from 46 to 90, I'm adding 44. As I go from 90 to 150, I'm adding 60. So those numbers aren't the same, but the difference of those differences is the same. So that's the deal with a quadratic sequence. The difference of the difference is common, is constant. So for instance, from 28 to 44, that's a difference of 16. 44 to 60, that's a difference of 16. So if I wanted to calculate the next term, I would have to add 16 to 60, which would be 76. And I would add 76 to 150, which would give me 226. And if I wanted to get the next term, I would add 16 to 76, which would be 92. And then I would add 92 to 226. So that's what makes it quadratic when looking at the terms. So the difference of the terms is not common, but the difference of the difference is common, if that makes sense. All right, so let's look at how we can find the actual explicit formula or rule for a quadratic sequence using the example that we just been using. All right, so let me clear this and let me rewrite the sequence we've been talking about, the quadratic sequence we've been talking about, which is 18, 46, 90, 150, and if you like, 226. All right. So how can I find its rule? Well, if the quadratic sequence is going to be of this form, an squared plus bn plus c, that means there's 3 things I don't know, because n is just going to be the variable. It just represents the position. I don't know a, I don't know b, I don't know c. And what did they teach you in algebra? You need as many equations as you have unknowns in order to solve a system of equations. So I have 3 unknowns, a, b, and c. So I'm going to need 3 equations. And so I'm going to construct 3 equations from the simple fact that I know that when n is 1, I should get 18. And when n is 2, I should get 46. And when n is 3, I should get 90. So again, if I know the sequence is going to be of this form, and I know when n is 1 is 18, n is 2 is 46, n is 3 is 90, then I can do the following. I can plug in 1 for n here. So watch me plug in 1 for n. So that'll be a times 1 squared. That's a, plus b times 1. That's b, plus c. And what that should equal is 18, because when n is 1, I should get 18. And I'll do the same thing for 2. I'll plug in 2 for n, and that'll be a times 2 squared. That's 4a, plus b times 2. That's 2b, plus c. And when n is 2, I should get 46. And then lastly, I'll plug in 3 for n, and that'll be a times 3 squared. That's 9a, plus b times 3. That's 3b, plus c. And that should equal 90. So there we have 3 equations. We have a system of 3 equations, and we need to solve for 3 variables. So it should be solvable. If a solution exists, we should be able to find it. Now, I didn't have to use the values when n was 1, 2, and 3, because you see as I'm sitting here, I have 5 values to choose from. I know the values when n is 4 and n is 5. Instead of 1, 2, and 3, I could have used when n was 3, 4, and 5, or when n was 1, 2, and 5, or when n was 2, 3, and 4, etc. In any combination you want of just 3. But it's generally ideal to use when n is 1, 2, and 3 if you know those values, because those are the first 3 numbers. They're the smallest numbers and most likely will be the easiest numbers to manipulate. So we want to do it as easy as possible. So what I'll do is I'll create an augmented matrix from these 3 equations, and I'll solve it. So I'm not going to necessarily, well, I know I'm not going to put the matrix in reduced row echelon form, but I'm going to do some elementary row operations to get it to a point where I kind of feel it's pretty nice to go ahead and solve and do a little back substitution. So I want to get it fairly close to reduced row echelon form. So I'm not doing a bunch of back substitution, but I'm definitely not going to go all the way to reduced row echelon form. All right, so let's go ahead and construct the augmented matrix, and that would be this guy: 1, 1, 1, 18, 4, 2, 1, 46, and 9, 3, 1, 90. There's our matrix. So let's go ahead and do some elementary row operations and solve this system. All right, let's clear a little space and let's get ready to do work. All right, so I'll tell you what I'm going to do first. What I want to do is I want to knock these 2 off. So I want to zero those 2 out. And so what I'm going to do is I'm going to take row 1. I'm not going to do anything to row 1. So row 1 is going to stay 1, 1, 1, 18. But I'm going to multiply -4 times row 1 to row 2, to get rid of this 4. And I'm also going to multiply -9 times row 1 to row 3 to get rid of this 9. So let's look at what happens. So again, if I multiply row 1 by -4, that will give me -4, -4, -4, -72. And I'm going to add that to row 2. So if you look at what happens, we'll get 0 there, and then we have -4 and 2, that's -2, and then we have -4 and 1, that's -3, and then we have -72 and 46, that's -26. And I'm also going to multiply row 1 by -9 and add it to row 3. So if I multiply row 1 by -9, that'll be -9, -9, -9, and 9 times 18. 9 times 18 is -170, 162. But I want to think of it as 9 times 10, which is -90, and -9 times 8, which is -72. Now again, that adds up to -162. But if I think of it like this, when I'm adding it to this, the 90 and the -90 cancel, and I'm just left with -72. All right, but anyway, let's go. So we're going to add -9 to 9 at 0. That's why we're doing it. -9 to 3, that's -6. -9 to 1, that's -8. And we already talked about down here, we're going to get -72. All right. So this is kind of my approach when using an augmented matrix to solve a system of equations. So I like to get rid of these 2 guys here. And then the next thing I would like to get rid of is this guy. And so to do so, I'm going to multiply row 2 by -3 and add it to row 3. So I'm going to leave row 1 alone. I think I need a little space on the side. I was going to write it underneath. Doesn't look like I have a lot of space under there. So let's utilize this space here. All right, so I'm going to leave row 1 alone. 1, 1, 1, 18. I'm actually going to leave row 2 alone. 0, -2, -3, -26. But I'm not going to leave row 3 alone. So what I'm going to do is I'm going to multiply row 2 by -3. So I'm multiplying row 2 by -3, which would turn its values into 6, 9, and 78. And I'm going to add that to row 3. And so what happens is, these two would give you 0, there's 0, and those two would give you 1. It's a beautiful number to get there. And those two would give you 6. All right. So from what I have right now, I can already see that C is equal to 6, because you have that 0, 0, 1, 6 there. So I can see that C is equal to 6. And some people would take that value of C and then back substitute to row 2 to get B, and then back substitute those both to row 1 to get A. But I'm going to just clean up just a little bit more before I start doing my back substitution. And the next thing I want to do is I want to get rid of this guy right here. And so to do it, I'm going to multiply 3 times row 3 and add it to row 2. So I'm going to leave row 1 and row 2 alone. Let's clear the other side. All right, so row 1 still remains unchanged. It's unwavering, 1, 1, 1, 18. Now for row 2, so again, what I'm going to do is I'm going to take row 3 and I'm multiply it by 3. That would be 0, 0, 3, 18. And I'm going to add it to row 2. So, the first guy is going to be 0, and then you got 0 and -2, so that's not changing the second guy. But the 3 and the -3 give you a 0 right there. And the 18 and the -26 give you a -8. All right. And again, I'll write row 3 as it was, 0, 0, 1, 6. Now it's where I'm ready to solve the system. So again, I can clearly see by row 3 that C is 6. I also can clearly see by row 2 that -2b is -8, which means b is going to be +4. And I'll use these values for b and c to substitute into row 1. And so that means that a plus b, so +4, plus c plus 6 equals 18. And so this is 10 here. Take it from 18, you get 8. And so that means that A is 8. So it looks like we have solved our system. And so if we look at what we have that A is 8, B is 4, and C is 6. So it seems like the system then would be 8n squared plus 4n plus 6. But we want to make sure this is indeed the correct system. So I'm going to double check, and I'm going to see if indeed if I plug in 1 for n, I get the first term. If I plug in 2, I get the second term, etc. So I want to remind you of what those terms were for the sequence. So the terms were 18, 46, 90, 150. We also had, 226 next. Really probably just going to verify the first 3 versus the first 4, the first 5. So let's clear some space and let's see if this rule we just found does indeed describe the given sequence. So what I'm trying to see is if I plug in 1 for n, do I get 18, and 2 get 46, 3 get 90, etc. So let's go ahead and do the calculation. So let's start when n is 1. Oops. So that would be A1. And it means I'm plugging in 1 for every n here. That would just give you the coefficient. So that would just be 8 plus 4 plus 6. That's indeed 18. That one works. Now A2, so that's plugging in 2 for n. So right here, I'll have 8 times 2 squared. That's 8 times 4. That's 32. And then 4 times 2, that's 8. That's 40 right there. And then you just have plus 6. So that's indeed 46. So that works. Let's try it when A is 3. So when A is 3, I'll have 8 times 3 squared, that's 8 times 9, that's 72, plus 4 times 3, that's plus 12. So that's 84 right there, and plus the 6. That is indeed the 90 we want. So since it was so much fun, so we got the 46, we got the 90. Let's go ahead and just plug in the 4 and see if we get 150. So if we plug in 4, this will be 8 times 4 squared. That's 8 times 16. That's 80 plus 48. So that's 128. Plus, what am I plugging in? 4. So plus 4 times 4, that's 16. That's 144 there. And plus 6, definitely 150. So check, check, check. So I hope you enjoyed this video as we explored quadratic sequences and how to find their rule or explicit formula. We will see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.